This week's topics included signed number representations and 2's complement arithmetic. So guess what? The experiments you'll be conducting this week will involve signed number representations and 2's complement arithmetic. So let's go ahead and look at our experiments for this week. The first one is a signed-unsigned binary number decoder. And what's really cool about this lab is you're going to get to combine the stuff that you've learned in your previous labs, and that you'll get to use your 7-segment display again, and you'll get to use the concept of modular design. So in this signed-unsigned binary number decoder, what you're going to do is use the 8 switches on your Nexus 2 board to represent a decimal number. Now those 8 switches could be interpreted as a signed number or as an unsigned number. And you'll use button 3 to tell you if you want to do a signed or an unsigned number. And then the display of the decimal value will show up on the 7-segment display. So you'll see the number. If you have 4 zeros and then a 0, 1, 0, 0, you should see a positive 4. But if it were signed, well, since it's a positive number, you'll also see a positive 4. But then if your number started with a 1, let's say it was 1 followed by all zeros, if that were an unsigned number, that would be a positive 128. But if it were a signed number, it would be a negative 128. And so you'd have to figure out what needs to be displayed. So in order to help you display these decimal numbers on the 7-segment display, we've provided a 7-segment decoder module that you can use as a component in your design. So again, the first way to approach this lab is to see, okay, how am I going to use this component and what other blocks do I need to make this whole design work? So you'll draw your black box diagram or your structural model diagram that show how all of your components are connected. Okay, so what is this 7-segment decoder module? So let's look again at the 7-segment display. If you recall, the 7-segment display is controlled by anodes and cathodes. And the anodes tell you which of the 4 displays you want on, and the cathodes tell you which of the 7 segments you want on. So you might have already thought to yourself, well, what if I wanted to display something different on each of these 4 displays? Because if I program my cathodes to be a certain number, isn't that what's going to be displayed on every 4 of the displays? Well, the answer is yes, that is correct, because you don't have an individual node to control each one of these in the separate 4 displays. So how do you go about putting a different value on each of the displays? Well, what you do is you multiplex the display, which means that you're going to send a value or a number to be displayed on the leftmost or the rightmost display, and then you're going to quickly turn that off and display something on the second one, turn it off, display something on the third, turn it off, display something on the fourth, turn it off, rotate back to the first one, display something on the first one, turn it off. And so if you make this speed at which you rotate between turning on and off each of the individual displays very fast, your human eye cannot detect that you're actually rotating or turning on and off between each of the 4 displays. And it will give you the appearance that you're actually sending 4 different values or 4 different patterns to displays at the same time. But what you're really doing is having this clock turn on and off these anodes and give different values to these cathodes to put different values on the 7-segment display. So that is what this module that we are giving you is doing. Let me go ahead and go through some of the code of this module. You don't need to worry about understanding it completely right now, but by the end of this course you should be able to fully understand this module and write something similar to it. Okay, so let me pull up the 7-segment display module. This was authored by Professor Brian Mealy, and we've been using it in this course for a while. As you can see, it was authored on in 2010. Okay, so it's important to note what the inputs and outputs are of this module. So we can look at that again in our handout. It's shown right here. There's the clock input, and this clock input is going to be linked up to your UCF file. If you look at the pin out, you can see that the clock, there's a clock on your board which runs at 50 megahertz. That's pin B8. So your clock is going to be an input to your overall module, and you will then connect that to pin B8 in your UCF file. Okay, so we've got the clock. We have the data input. The data input is the 8-bit value that you want to have displayed. Valid, as described in this header, is if valid is equal to 0, you will see 4 dashes on the display, and if valid is 1, you'll see the number appear on the display. Then you have the sign input, and again, if sign is a 1, a minus sign appears on the leftmost, and if sign is a 0, no minus sign appears. Then we also have the display enable, which are the anodes, and then the segments, which are the cathodes for the 7-segment display. And in this case, ALU val is the same thing as what was referred to as data in this diagram. So that should have matched, but anyway. So those are your inputs and outputs of the 7-segment decoder. And all you have to do is link up the inputs and outputs of whatever logic you create to this 7-segment decoder component. And basically you're going to have to send it some data from your circuit, and you'll have to send it a valid signal and a sign signal. So of course, if you're doing a sign number representation and the number is negative, you'll have to give the sign bit a 1. And in this case, you'll always want to send valid a 1 because we always want to see the number displayed. In the next experiment, you'll see that you'll have to determine if the operation or the addition is valid or not valid and assign valid appropriately. Okay, so this 7-segment decoder, what does it do? So we've declared the entity with all of its inputs and outputs, and then you'll see that it has 2 components to it. And these components are actually declared within this file itself. So instead of needing to add the files for these 2 components, they're already within this 7-segment file. So you don't need to worry about that. And how you do that is I'll show you if you scroll down. You can see that this bin2 BCD-conv, which is a component of the 7-segment decoder, you can list it in the same file as long as you put the libraries on top of wherever you declare subcomponents. What I really like to do is have each of my entities in a separate file and then just include all those .vhd files in my project. But if in this case, if they're nicely contained within this, you can add your component definitions into the same file by putting the libraries to say, okay, look, I'm actually sort of creating a different file with a different component. And you can see that as well with the clock. Here's your other component, which is, this is like a separate file that has the libraries to denote that. Okay, so we got that out of the way. We have 2 components. Instead of having to add the files, they're just declared here because we've sort of pseudo-added 2 files with these libraries. And then what is this thing doing? So we have the 2 components, we have our intermediate signal declaration, and we port map our components, and okay, so what else is going on here? This should look familiar to you. This looks like your BCD to 7-segment decoder, which tells you, okay, if your digit is a 0, what segments are you going to turn on to make it look like a 0? If the digit is a 1, what segments do you turn on? So this should look just fine. And this then tells you what display to actuate. So you can see this is turning on the rightmost display, the next display, the next display, and the leftmost display, depending on this variable called countDig. And then there's all this fancy stuff going on, which I'm just going to briefly talk about what it's doing. So your input, if you recall, the ALU val input is 8-bit vector. So the largest decimal value that you could represent in unsigned would be 255, right? Because that's going to be 2 to the 8th minus 1, which will give you your highest representation. So you can represent with 8 bits any number in unsigned from 0 to 255. So this first part of the process is this is doing the blanking of the two most significant bits. So let's say you wanted to display the number 9. Well, the number 9 would indicate that you only need the least significant bit displayed, and the most significant bit and the middle bit just need to be blank. You don't need to write 009, you just write 9. Whereas if you had a number like 128, you'd have to have all three of those bits, or all three of those digits displayed. So you'd have to have the 1, which is the most significant digit, and then the 2, which is the middle most significant digit, and then the 8, which is the least significant digit, all displayed. So this is blanking out the two MSBs if you have a digit that's less than 10, or if you have a number that's less than 10. Okay, so this one then is then checking what's going on with your valid and your signed signals. So if your valid signal is a 1, then you want to actually display your data. And then it determines if your sign is a 0, well, you're going to be blanking out that most significant digit display because you're not going to put a negative sign or a dash there. But if it is, then you're going to end up putting the dash. So that's what this is doing. If it's not valid, then you're just displaying dashes. So that's what this is doing here. It's setting your digit that you want to be displaying to a code for the dash, which you can then check back up there. So 1110 should be our code for the dash. 1110 is our code for the dash, as you can see. So this will give you a dash. Okay, so that's what that's doing. Now, how are we displaying the number that's in 8 bits into a decimal format? Well, it's using a very similar approach that we've learned for converting binary to decimal. And so what we're doing is we're first figuring out what is the decimal number represented by these binary digits. So as you can see here, you have your 8 binary digits coming in, and if your most significant bit is a 1, that has a magnitude of 128 because it's the most significant digit. This is exactly what we did when we were converting binary to decimal. We just started adding up all these powers of 2. So if the 6th bit was a 1, you're going to add in 64, etc. So then this value, count total, is going to have your total decimal value that you want to display. Then, so let's say your total decimal value is 128. So that 1 is going to be your most significant digit, which can be a value from 1 to 2. So you could either have a number that's less than 10, that's greater than 100, or greater than 200. So it can go up to a maximum value of 2 because your maximum number that you're creating is 255. Then you have your MSD, which is the middle digit, and then your LSD, which is your least digit. So this is showing you, okay, now that we have our number, let's say it's 128, we're going to calculate what is the most significant bit, or most significant digit. And as I was telling you, this can only be 1 to 2. So it's saying if your count is greater than 0 and less than 100, you're going to add 1 to this. So it's going to start out of 0, but if you're greater than 100, you'll add 1. Then you're going to go to the next part of the loop, and okay, so you subtracted 100, so let's say your number was 255. So your most significant digit is now 1. Then you subtract 100, so you get 155. And okay, it's still greater than 100, so you get your 2. So now you know that your most significant digit is a 2. So you can kind of get an idea of how it's figuring out, okay, now that I've got my number that I've figured out up here, now I have to parse that out to know which thing I want to display. So we've created our MMSD, and then we need to get the middle digit, which can go from 0 to 9. And so this is then taking your count and just subtracting 10 every time to figure out, okay, what is this middle digit going to be? And then you have your least significant digit, which is once you've subtracted out the hundreds and you've subtracted out the tens, you're left with just the ones place. So if it's a 9, you're going to get a 9, down to, well, if it's a 2, you're going to get a 2, etc. And then, so you've got your least significant digit in the form of a BC, or yes, BCD. And then you might have your middle digit. Now that you've figured out what it is, you need to convert it to a BCD. And then you also have your most significant digit. You need to convert that to a BCD. And then you're good to go. So these values, LSD out, MSD out, and MMSD out, are all tied to the outputs of this subcomponent bin to BCD converter. And then if you look at how these are mapped, let's find it back up here. There's our component declaration and our port map. They're then mapped to these values MSD. And then you'll see below that these values, MSD, are mapped to variables of the same name, and we'll get into what variables are later on in this course. And then those get mapped to the value digit. So the thing is, okay, now that we know our 3 digits that we want to display, we have to display them one at a time. And so it gets sent to the digit, and then once it gets sent to the digit, it's the digit that then gets displayed to the segments. Whew! Okay, so yes, I know that's a lot to handle, and I don't expect you to get this right away, but let me just tell you, later on in this course, stare at this file again and things will start to make sense. You kind of have to just, take some time, stare at it, figure out what's going on, and it will start to make sense. It took me quite a while the first time I looked at it to be like, what in the world is this doing? But now I have a pretty good understanding of it, and you will too if you spend some time with it. But for the purpose of this lab, you actually don't even need to have a clue what this thing is doing, because the beauty of digital design is you could be handed a module, and all you need to know is the inputs and outputs of this module, know what it does, not to any detailed level, just have a general understanding of, oh, this module is going to take my 8-bit binary number and put it on a display for me. That's great. I can just use it. So you can just use it in your design and not have to worry about the inner workings of it, which is really cool. Okay, so you're going to be using this, you're going to be making that binary decoder, and then guess what? You're going to do one more experiment that's then going to use this module again, but have you practice using a signed binary adder subtractor with validity detection. So that's where your valid signal is going to come in. So these 2 experiments are a little more lengthy than perhaps some of the other ones we've had so far, but they are very valuable and really show you the power of modular design and really have you get a little more familiar with using signed numbers and adding and subtracting them. So for this experiment 12, be sure to write down a list of test cases for yourself, so that way you know what values you expect if you're adding or subtracting a signed number, what would be valid or not valid, so you can appropriately test your circuit. Alright, have fun!